Okay, we're continuing with Chapter 6 in the Trigonometry textbook. In this video, we're going to go through the second section, which discusses trigonometric equations. In the previous section, we looked at trigonometric equations where the argument inside of any of the trig functions involved in the equation was just an x. So like sine of x, cotangent of x. Now, in this section, we're going to consider equations where the argument is something different than just x. So, sine of x divided by 2, etc. All right, in this section, we discussed trigonometric equations that involve functions of half angles and multiple angles. So like a half angle, it's sine of 1/2 of x, tangent of 1/2 of x, and then multiple angles is sine of 3 times x, etc. Solving these equations often requires adjusting solution intervals to fit given domains. Okay, so we'll see what they mean by that as we go through these examples. So equations with half angles. Solve 2 times sine of x divided by 2 is equal to 1. 2 times sine of x divided by 2 is equal to 1. So yeah, we actually, in the previous section, we looked at an example problem at the end of the previous section where we got a sense of how we're going to have to approach a problem like this. So, okay, let's divide both sides by 2. So now we've got sine of x divided by 2 is equal to 1/2. Okay, now we can get take the inverse sine of this entire equation. So we've got x divided by 2 is equal to inverse sine of 1/2. Okay, and so now you can see where this is a little bit different in the sense that previously we would just have theta or x is equal to, and then we'd have the inverse trig function. But now it's going to be, x is going to be whatever the inverse trig function values are times 2. So it's a little bit different. So, okay, inverse sine of 1/2, we can think about the 30, 60, 90 triangle. So 1 root 3, 2. Sine of 30 is 1/2, so this is positive 1/2. So we've got x divided by 2 is equal to, so 30 degrees, or, okay, so sine is positive in quadrant 1 and quadrant 2. So what angle in quadrant 2 has reference angle 30 degrees? That would be 150 degrees. And then that's it for 0 to 360, but then also any angle that's coterminal with these. But you see the difference for these types of equations is that the final answer is like 2 times 30 or 2 times 150 or 2 times any angle that's coterminal with these angles. So it's x is equal to, so 60 degrees and 300 degrees. But then does that mean that it's 60 degrees, 300 degrees, and any angle that's coterminal with 60 and 300? I guess maybe we could say that. So 360 plus 60 is 720. And 720 divided by 2 is 360. Is 360 a part of this? No, it's not. So you see, you can't really say that. You can't say 60 degrees, 30 degrees, and any angle that's coterminal with these angles. It's really, you have to say it's 30 degrees, 150 degrees. It's 2 times 30 degrees, 150 degrees, or any angle that's coterminal with those. That's the answer. I mean, it's not a big deal. It's just, you just have to make sure you know what you're doing. You understand, like, you have to write out the final answer in a way that you make it clear to yourself what the answer is. Okay, and so that's what they do here. They go through that process, and then for part A, they just give the solutions between 0 and 2 pi. So that's 60 degrees and 300 degrees. That's what these are in radians. And then they do for all solutions, and they just write this in a mathematical way. I don't know how you would represent this mathematically, that what they're talking about here is the answer of 30 degrees, 150 degrees, and any angle that's coterminal with those times 2. So, okay, you'd say it's 2. The answer, all solutions to this equation, 2 sine of x divided by 2 is equal to 1, is 2 times 30 degrees, 150 degrees, or any angle that's coterminal with those two angles. That's the general answer here. Okay, equations with multiple angles, it's going to be the same idea. So this is really not that difficult if you understand exactly how we solved all the problems in the previous section. This is just a simple extension. It's just a special case where you've got something multiplying the argument in the trig function. But it's the same thing though. It's just you have to understand how to evaluate the inverse trig function and all the possibilities. But then that's if you understand that, then this is really simple. So it's not simple if you don't understand inverse trig functions and all their potential solutions and how to solve trig equations from the previous section. But if you understand those two, then what we're doing here is easy. So solve cosine of 2x is equal to cosine x over the interval 0 to 2 pi. Well, actually, we're not quite done. It will get a little more complicated. So yeah, if we had a linear case, if we come back, this was a linear case with a trig function where you had an argument that wasn't just x. This was a linear case in the sense that we could say, u is equal to sine of x divided by 2, and we're left with this linear equation that we could solve. So, that's easy. You just take the inverse trig function of both sides, and you write the answer. But what if we have double angles or multiple angles, but now it's not linear? So that's a little more complicated. So you see it's saying cosine 2x is equal to cosine x. So yeah, this does get a little more complicated. This is, what do we do here? Well, we're going to take advantage of the trig identity. So with multiple angles and half angles, we've got the half angle formulas, the double angle formulas, and we've got the sum to product the sum and difference formulas. Those combinations of those three, we can break something, a trig function down into the trig functions that are just single angles. We learned all about that in the previous chapter. So we can take cosine of 2x and write it as, we have 3 options with cosine of 2x. So to make it everything, it would be nice if we have everything as a cosine, because then we have one trig function to deal with. So let's write cosine of 2x as 2 cosine squared x minus 1. So 2 cosine squared x minus 1 is equal to cosine x. And now we can say that if we say u is equal to cosine x, then we've got 2u squared, and subtract cosine x from both sides, minus u minus 1. And that's just a quadratic. So let's come over here. That would be, I guess we could factor this. So, well, we have to do grouping first. So let's see. 2u squared minus 2u plus u minus 1 is equal to 0. Okay, so 2u, u minus 1 plus u minus 1 is equal to 0. So 2u plus 1 times u minus 1 is equal to 0. So we've got u is equal to minus 1/2 and u is equal to 1. So, but u is equal to cosine x. So cosine x is equal to minus 1/2 and cosine x is equal to 1. And we just go from there. This is just like what we solved in the previous section. So I'm not going to find x, but because we know how to do that. Okay, so that's another method if we're dealing with double angles, triple angles, whatever. Like we could write a triple angle. If we had cosine of 3x, we could write that as cosine of 2x plus x, and then break that up. And you could just break it down into all single angle trig functions, and then solve it like we did in the previous section. All right. caution, because 2 is not a factor of cosine 2x. Cosine 2x over 2 is not equal to cosine x. Yeah, of course. Yeah, do not do that. Do not say that, yeah, this, you would look very silly if you did something like this. Started here and you did no, absolutely not. Okay, solving an equation using a double angle identity. So yeah, how would we do something like this? 4 sine theta cosine theta is equal to root 3. Well, so in the previous problem, we broke down a double angle to get to all single angles so we could solve the equation. However, we saw that sometimes it's not that bad if you solve the equation. So if we come back, like it's not like we had sine of x divided by 2 here. Well, we could have used the half angle formula to break that up, but we didn't need to do that because it was already linear. If it's linear, then just go ahead and solve it and use the inverse trig function to get the variable out, right? So if there's ever a scenario where you see that you can make the equation linear, regardless of if you have a double angle, single angle, half angle, whatever, then do that automatically. So we see here that we can say that we know that 2 sine theta cosine theta is equal to sine of 2 theta, right? So we can, if we factor out a 2 here, right? So we can say 2 sine 2 theta is equal to root 3, and absolutely we want to do this because now this is linear. Inverse sine of both sides. So 2 theta is equal to root, or inverse sine. So 2 theta is equal to inverse sine of, okay, and so same idea as what we did in the first problem, root 3 divided by 2. So let's see. $30, $61, root 3, 2. So root 3 over 2, let's see. That's sine of 60 is root 3 over 2. Opposite over hypotenuse. So we've got 2 theta is equal to 60 degrees. And then in the second quadrant, what angle has reference angle 60 degrees? That would be 90 plus 30, 120 degrees. So the answer is 2 times 60 degrees, 120 degrees, or any angle that's coterminal with those. 2 times those angles. See? All right, note, solving an equation by squaring both sides may introduce extraneous solutions. We use this method in example 4, and all proposed solutions must be checked. So it's the same kind of idea as we learned in the previous section. You're trying to see the parallels between the trig equation you're solving and a corresponding algebraic equation. You really want to do that, right? Like here, we had a quadratic. Sometimes, like here we turn it into a linear. I'm probably going to make a whole separate video because this is kind of confusing, going through the general strategy to solving trig equations. Actually, I am going to do that. So, okay. What about, so tangent of, let me make some room here. Okay, so tangent of 3x plus secant of 3x is equal to 2. So, okay, there's a couple of options I can think about here. You know, one, you always want to consider the fact that can you manipulate the equation and then use trig identities to simplify. So with tangent and secant, we do have a relation here, a Pythagorean identity with tangent and secant. And so maybe squaring both sides, something to do with squaring both sides would be useful. And I mean, that's what they're going to do. They just mentioned that. So without looking at the solution, I wonder, I'm assuming they might subtract secant 3x from both sides, something like that. Yeah, that's what they did. So but I mean, if you didn't see that, you could just try something else and then come back and try, and then just keep manipulating it. So the idea is when you do this, you're going to potentially get a trig identity that will simplify it. But the point they're wanting to make is that what we know in algebra is when you square both sides of an equation, which is most commonly done with a radical equation to get rid of the radical, then you have to look at extraneous solutions. So it's going to be the same idea here. But it'd be, if you had an absolute value equation that had trig functions, then it'd be the same idea. There could be extraneous solutions there. So tangent squared 3x is equal to, so we're going to have 4 and then minus 4 secant 3x plus secant squared of 3x. Okay, so let's see what trig identities. So secant squared minus tangent squared is equal to 1. Okay, so we can subtract tangent squared 3x from both sides. So we'll have secant squared 3x minus tangent squared 3x. That's going to be equal to 1. So 4 minus 4 secant 3x plus 1 is equal to 0. So we can see that's going to result in 4 secant 3x is equal to 5, and there you go. Now we've converted this into a linear trig equation with a triple angle. So secant 3x is equal to 5/4. So we're going to have 3x is equal to inverse secant of 5/4. And you just solve it from there. Okay, an application. A piano string can vibrate at more than one frequency when it is struck. It produces a complex wave that can mathematically be modeled by a sum of several pure tones. When a piano key with a frequency of F1 is played, the corresponding string vibrates not only at F1 but also at the higher frequencies of 2 times F1, 3 times F1, etc. F1 is the fundamental frequency of the string, and higher frequencies are the upper harmonics. The human ear will hear the sum of these frequencies as one complex tone. All right. Suppose that the A key above middle C is played on a piano. Its fundamental frequency is 440 hertz, and its associated pressure is expressed as, okay, by this sinusoid. The string will also vibrate at these other frequencies. The corresponding pressures of these upper harmonics are as follows. Okay. The graph of P is equal to P1. The sum of all of these can be found by entering each P1 as a separate function and graphing their sum. The graph is shown here. It's the sawtooth periodic wave, but it's the sum of all of these different sinusoids. Approximate the maximum value of P. Okay, so they just do this graphically. You know, you've got these different amplitudes, but they do a graphical approximation of the maximum value of the resulting sinusoid. At what values of t is equal to x does this maximum occur over 0 to 0.01? Okay, and so they just match up the peaks with the corresponding x values, and it looks like they do that graphically as well. So I guess they're just trying to, we're not doing any actual math here or analytic math. It's all graphical, like numerical math. They're just trying to illustrate an application of something with a multiple angle of a trig function, and then you have different, you could be interested in all, and when you do the inverse sine, there's a bunch of different values, right? There's a different answers, like infinite number of answers, and that's the idea here, that these multiple frequencies, that's an illustration of how, you might wonder, well, when does this, you have all these different solutions to a trig equation, when does, well, usually your answer is going to be one or two of those solutions based on the specifics of your problem. But here's an example where you have, all these different frequencies, the fundamental and higher frequencies. That's what the multiple answers of the trig equation correspond to.